So in this video, I'm going to talk about the minimization or optimization in SciPy using the minimize function. And basically what we're going to talk about is minimizing functions of one or multiple variables. And the syntax is very much similar to the root command. And so let's just do an example. So we can do define f of x, and maybe we want to return x minus 1 squared. And so this function by inspection is just going to have a minimum at 1, right? Because that's when the function is going to be equal to 0. But I just choose this as a very simple function. So we can set sol is equal to minimize. We're going to put it in our function, and then we're going to give an initial guess. So maybe I'll give the initial guess 3. And then I can print the solution, which is sol.x. And we see that the minimum is at 1. And if we want to look at what the minimum value is, we can do sol.fun. And if you look at that, the minimum value is 0. And we can see this by inspection. Actually, we could just plot up this function. So we could do np linspace 0 to 2. Let's do 1,000 points. And we can do plt plot x, f of x. And then we can do line width is equal to 3. And color is equal to red. And then do plt show. And you see that we have our function here, and then we have the minimum at 1, and that value is equal to 0, which is what the minimize function is determining. Okay. So the way these algorithms work is you have an initial guess. So maybe if we initial guess 2, is basically they do a local search and they pick a direction that's downhill, and then they kind of march downhill. So initially the function would be up here at 3, and then gradually it's going to migrate or iterate until it finds this bottom point, and it's basically looking for a point where the derivative is equal to 0. That's at least in the unconstrained case. In the constrained case, it's a similar idea, except you have to modify the objective function with Lagrange multipliers. We're not going to talk about the theory, but in a second, I'll show you how to add constraints to the problem, where we kind of limit the range of decision variables we're looking at. Right now, we're looking at infinite number of decision variables. Similarly, we can also do a two-dimensional function. So we could do f of x, and maybe we want to return x minus 1. Let me slide up here. We'll have x of 0, which is our first decision variable. So maybe we'll do x of 0 minus 1 squared, and plus, we'll maybe do x of 1 minus 2 squared. So just by inspection, this function is going to have a minimum at 1 and 2. And if we want to solve it, we're just going to do sol.minimize f, and we'll do initial guess. Maybe we'll guess 5, 5. And then we can print sol.x. In this case, it's going to be a vector. And then we can print the minimization function, or what the value is at the minimum. And again, by inspection, we have this function 1 and 2 as our minimum, especially if we round this. And then our minimum value is basically 0 to numerical precision. So that's kind of the general format for minimization, at least unconstrained functions. So let's consider this function again, where we have f of x. And maybe now we want to add the constraint that x is between 1 and 3. And so what we can do is add basically, we can just come over here and we can put bounds. And then we're just going to limit the variable between 1 and 3, right? And this has to be, let me just run this. Whoop, I forgot the second quote. So this has to be a list of lists. So we run it, and now we look at our solution. And what am I doing wrong here? Yeah, and we get the solution at 1, right? Because if we bound this between 1 and 3, the solution is going to be at 1. We could also do a bound between, maybe let's make it more realistic, 2 and 5. And so we could do 2 and 5. And this is obviously going to be, the minimum is going to be equal to 2. But now we've minimized the function at 2, and then the objective function is 1. The reason why it's a list of lists is because when we do multiple variables, we'll have to add another range for the second variable. So let's just do that example. And so maybe we want, in this case, maybe we want x of 0. We want this between, maybe 4, 3, and let's do 7. And then maybe our second variable, we want x maybe we want it less than or equal to 3, right? So it's going to actually have no lower bound. And so the way we do it is we have our initial guess, and then we would take our bounds part. And when we have our bounds, it's a list of lists. So our first variable, we're doing 3 and 7. And then our second variable, since we have no lower bound, we're just going to put a none here. And then our upper bound is 3. And we run it. And in this case, our solution is going to be 3 and minus 3. So basically, we're hitting this lower constraint over here. And then we're hitting this upper constraint here. And this is actually x of 1. I'm sorry about that. And so that would be kind of another way of putting kind of bound constraints in this problem. The other thing we can do is we can do kind of constraints where the constraint is satisfied by a function. And so let's just grab this example again. So we have f of x. And maybe we want the constraint that x of 0, we want x of 0 plus x of 1, and maybe we want to set that equal to 2. Right? So what we're going to do is define a new function called constraint of x. And what we're going to do is kind of, as before, in that we're going to just rewrite this constraint as x of 0 plus x of 1 minus 2 is equal to 0. Right? And so we're going to return basically the part that we want equal to 0. So we're going to have x of 0 here plus x of 1. And then we're going to set this equal to 2. And so I'm going to add, so the way we're going to pass in constraints is as a list of a dictionary. And so what we're going to do is we're going to do type, and this is going to tell us the type of the constraint. I have a sore throat. And we're going to force it to be an equality constraint, right? So this is an equality. I'll do an inequality in a second. And then we're going to do the function, and then we're going to put in our constraint function. And so when we want to minimize this, we're going to do sol minimize. We're going to minimize our function. Minimize. We're going to give our initial guess. Maybe we'll do 3, 3. And even though it doesn't satisfy the constraint, we can still just give it an initial guess. It'll figure that out. And then we can do constraints is equal to cons. And then we can print sol.x. And then we can print sol.fun. And in this case, we get our answer, which is 0.5 and 1, right? So that's forcing the equality constraint. So that satisfies the equality constraint. And then this is our minimum function. And if we wanted to add another equality constraint, we just put a comma here and add, another function in the list. The other kind of function we can add, and let me just grab all this, is we can do inequality constraints. So maybe we want the function that x plus 1 is bigger than 2. And the way we're going to write this, so all equality constraints in this problem are going to be non-negative constraints. So we're going to write this as x of 0 plus x of 1 minus 2 is greater than equal to 0. And so the reason why I did this is I don't have to change the function. And if we're making it greater than equal to 2, we just put an inequality constraint there. So we replace equality with inequality, and then we run it. And now basically we're going to get 1 and 3 is our solution, right? So we're forcing them to be bigger than 2 if we add these two functions together. Maybe we could also change it if we want it to be bigger than 3. And here we're going to get 1 and 2, and that would be our inequality constraint. We could also add another constraint. Maybe we have con 1 here, and maybe our second constraint is maybe we want our two variables equal to each other. So we want x minus x1. And this is basically saying that we want x of 0 is equal to x of 1. And then we would just add, so we'd have con 1, which is our inequality constraint. And then we would add our second inequality constraint. And so this is an equality constraint, right? And then this one is an inequality constraint. And then we have our two constraints. We run it. And now we have our solution. Here, the two solutions are forced to be equal to each other, 1.5 and 1.5. They also satisfy that the two solutions, when we add them together, are bigger than or equal to 3, right? So they're at the value 3, so we get our solution there. We can also add bound constraints to this. We could also do bounds over here. And maybe we could force the variables all to be, bigger than 4. So we can do none for the first one, and then the second one we also want bigger than 4. Right? So we have no upper bound, but just a lower bound. So we can start adding more and more constraints, and here we get our 4-4 solution in the problem. You know, if I made the second one bigger than 5, and the first one's bigger than 4, we're going to get back the solution 5, 5. So that's just a quick overview of minimization in Python. In the next video, I'll talk about you know, how would you do maximization problems, which is pretty simple. And then what we'll do, the third video, which will be posted later or posted soon, I'll go through the examples, and I'll actually go through example 4 that I posted on Compass. If you have any questions, please post them to the comment section or on Piazza. Thank you.